Welcome back. Today we're going to talk about equations in two variables. Okay, equations in two variables are just exactly like what they sound, right? So we have been looking at equations with just one variable. And when you have equations with just one variable, you often have only one solution. Okay, we've seen situations where there's more than one solution with absolute value equations. There's two solutions. Some equations have no solutions, and some one variable equations have infinitely many. But for the most part, they usually have one solution. Equations with two variables are going to have infinitely many solutions. All right, and we write the solutions to two variable equations as ordered pairs. All right, ordered pairs means the position that you use in the pair is unique. So for instance, the first position here is not the same as the second position. So the number 2, 3 is not the same as 3, 2. All right, this is things that you've been working with since like 6th grade. So you sort of know this already, but just to define it, we say ordered because the order matters in this pair. We often write two variable equations using variables x and y, and we usually denote them as x, y. Now this is going to link in with graphing these equations. So that's why we use the variables x and y, because we have in the Cartesian plane, we have x and y axes. Okay. If you want to tell whether an ordered pair is a solution to an equation, so two variable equations here look like 3x plus 5y equals 15, where you have x and y here. And if I want to determine if this ordered pair 8, 1 is an ordered pair, if this ordered pair is a solution, remember this is x, y, then what I can do is just substitute 8 in for x and 1 in for y and see if it makes the equation true. So here we can go 3 times 8 plus 5 times 1 and ask ourselves, is that equal to 15? So there's sort of a question mark at this equal sign. So 24 plus 5 does not equal, I can already see it doesn't equal 15 because it's 29. Okay, so the answer for this one is no. This ordered pair is not a solution to this equation. Okay, so remember, you're annotating alongside these steps. You are saying that what you're doing here is you're substituting the 8 in for x and the 1 in for y because it's an xy coordinate, right? That should be an annotation along the side of this. Okay, again, let's check the ordered pair 0, 3. So I'd substitute 0 in for x and 3 in for y. So this is 0 plus, and again, I'm going to put a little question mark because it's a question whether or not they're equal to each other. Okay, so question mark. Well, 0 plus 15 is equal to 15, so yes, the answer is yes, the coordinate 0, 3 is a solution to this two variable equation. Okay, let's check this one. So remember, when we substitute a negative value in here, let's use some parentheses because we're indicating that the entire base is negative. This is very important when you have a negative number and you're raising it to a power. Because a negative 5 squared ends up being negative 5 times negative 5, which is positive 25. And I should really have this question mark here. Well, 25 minus 2 is equal to 23. So yes, this ordered pair is a solution. Okay, and again, let's just put this, just to make sure, I'm going to put parentheses around the 5 squared because I just want to, I don't really need them. I don't end up needing them, but it's a good habit to get into when you're raising something to a power and you're substituting a value in for the base. So is this true? Well, 25 minus 2, is it true that it's equal to 23? Yes, it's true that those things, are equal to each other. So yes, again, these two ordered pairs are solutions to this two variable equation. So that's, if you're ever asked to determine whether an ordered pair is a solution, then this is how you do it. You substitute the x and y values in. Now note, when you say ordered pair, again, they're ordered. So this only gets substituted in for x, and the second value only gets substituted in for y. Okay, you're not able to switch them around because the order matters in this pair. So I just want you to recall there are two in the two-dimensional coordinate plane, right? So this is a 2D coordinate plane. The 1D coordinate is just the number line, right? The real number line is the is the one-dimensional coordinate, which means you only need one number in order to tell where you are in the one-dimensional system. So for instance, I could graph 3 pretty easily on the number line because I know exactly where that is. It is right of 0 by 3 units, right? In the two-dimensional system, I have two axes. I have a horizontal axis. So note that the word axis this is a singular form of the word. The plural form of the word is axes, with an E here instead of an I. So there are two axes, and there's one axis. Okay, that's singular and plural. So you have the horizontal axis, which is the x-axis, and you have the vertical axis, which is the y-axis. When you place them perpendicular to each other, so these literally just make a right angle. The x and y axes are perpendicular to each other. So it creates 4 separate quadrants, or 4 separate spaces, and we call them quadrant, quad with the prefix of quad meaning 4. So we label them starting in the upper right area. We label this quadrant 1, and we label it with Roman numerals. Okay, and we go around in an anti-clockwise or a counterclockwise manner. We label them in a counterclockwise manner. So we say this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Okay, again, note the Roman numerals here. Now, the signs of the coordinates in the two-dimensional system. So in two dimensions, we need 2 coordinates here in order to tell an exact location of a point. When you get to graphing 3-dimensional coordinates, you're going to have an x, y, and z axis. So you're going to have an x, y, and z coordinate in order to tell a particular point in a 3-dimensional space. But for us, we're going to stick with the 2 dimensions for a couple of years. So every coordinate here has a sign. So in quadrant 1, both the signs are positive. In quadrant 2, it's because it's to the left and above. So left meaning left is negative on the x-axis, and above is positive on the y-axis. So it's negative, comma, positive in terms of signs. In the third quadrant, you are negative for both coordinate because it's left and below the x. It's left of the y-axis and below the x-axis, so it ends up both being negative. And in quadrant 4, only the y-coordinate is negative. So make sure that you have this in your notes because it's a pretty key part to trying to figure out where points are located or how to graph to. So today we're going to look at creating equations and translating the equations into the geometric form of the equation, which is the graph. So let's say that I ask you to think of 2 numbers that add up to 6. Well, this can be easily represented by an equation like x plus y equals 6. And I could think of some values that work for this equation here by determining some values for x. So let's say that I choose an x. We're often drawn to whole numbers, so let's pick the whole number of 3. Well, y would have to be 3 in order for them to add up to 6. I could do 2 and 4, and I could do 4 and 2. Okay, I could do 1 and 5, and 5 and 1. I could do 0 and 6, and 6 and 0. I don't even have to stick to the positive whole numbers. I can go to the integers, -1, and this would have to be 7. I don't even have to stick to the integers. I can actually just go into the rational numbers, or I can go into fractions because some rational numbers are also integers. So I could say 1/2 here, and this would be 5½ here. Okay, so there's lots of different numbers. There's actually an infinite amount of numbers that would work in this case right here. So all of these numbers that we wrote down in this table, they all work to be substituted back into this equation in order to get the solutions to the equation. So if I made these xy coordinates here, and I made them like 3, 3, right, and 2, 4, for instance, all of these, this whole column to the right here, these are solutions to the equation. Now, they could just remain as solutions here, like algebraic solutions, but we could also transfer them into a graph, okay? By the way, the graph is called a Cartesian plane, named after a mathematician named René Descartes, who first thought of representing solutions to equations with 2 variables geometrically. He was the first one who really thought about putting them on a graph to see what the graph looked like. So we can thank Descartes for this sort of representation. So here, if I graph them, let's graph 0, 6 first. So 0, that would be 0 on the x-axis, and up 1, 2, 3, 4, 5, 6 here. And then I could also have 6, 0. So 1, 2, 3, 4, 5, 6. This is 6, 0. I could have 1, 5, that would be here, and 5, 1, that would be here. I could have half here and 5 and a half, that would come between the 2 points. I could have negative 1, 7 here. That's another point. So what you're going to see is when you graph all these points, they actually land on this line. Okay? So I'm going to draw the line on this between these points. And actually, not only are these solutions, the points that we wrote down here, not only are they solutions, but there is an infinite amount of solutions. So I'm actually going to extend my line into the furthest areas for the graph that I've created here. So always, that's a good thing to note, always extend your line to the edges of the graph paper that you have. And I'm actually going to place arrowheads on the end of the line, indicating that this line continues on forever, right? Making sure that it's a line instead of a line segment. A line segment has 2 endpoints, and a line goes on infinitely in both directions. So what I want you to notice is that not only are the points that we plotted they all are collinear, which means they all fall along the same line, that I can actually pick out a point, any of the points on here, and I could find the coordinates of this point. So this point would be 1, 2, 3, 4, 5, 6, 7, 8. So this would be 8, comma, and then negative 2. So what you're going to notice about these points is that 8 plus negative 2 is 6. In other words, these points are solutions. So not only are the points that we created solutions, but every single point on this line is a solution to the equation that we created. Now think about what a line is. It's actually made up of an infinite amount of little tiny points here. So all of the points on this line, there's an infinite amount of little tiny points, even points that don't fall along the intersection of 2 grid lines, right? There's this point, there's this point, there's this point. There's all these little tiny points that don't fall along integer values for coordinates. Every single one of these points, if I were able to pick out exactly what the coordinates were, what I would know for absolute certain is that the x coordinate added to the y coordinate is going to be equal to 6. Okay, so all the points along the line are solutions. Also, you know that any point that's not on the line is not a solution. So for instance, if I picked out this point is negative 1, 1. Well, the x coordinate plus the y coordinate is not equal to 6. So that's something I absolutely know for certain. So there's 2 things to pull out here. Every point on the line is a solution, and every point that's not on the line is not a solution. Okay? Let's go on to a word problem. Let's say that the entrance fee for Mountain World theme park is $20. Visitors purchase an additional $2 tickets for rides, games, and food. So we have 2 costs here. We have a variable cost, which I'm going to put in yellow, and we have a initial cost, which is $20. So this is the initial cost, and this is the variable cost. And let's put a little key here. This is the initial, and this is the variable or the rate of change cost. Variable meaning it depends on the amount of tickets that you buy, right? So here I'm going to make an equation. If y is the total cost in dollars, then in order to get the total cost, I'm going to take the variable cost, so it's the amount of tickets times 2, so it's 2x, plus the initial cost, which is $20. So you only pay a one-time fee of $20, but then for every ticket you buy, it's $2. Okay, so I'm going to use that equation to fill in the solutions here. So for 2 tickets, that's 2 times 2, which is 4, plus 20, which is 24. For 4, it would be 8 plus 20, which is 28. For 6, it would be 12 plus 20, which is 32. And for 8, it would be 16 plus 20, which is 36. And I actually put 30, whoops, I just switched them both around. So this is 32 and this is 36. Now if I were to graph this, so I have a nice graph here, the number of tickets is the x and the cost is the y because the cost depends on the number of tickets. I could take first 0, 20 would be 0 on the x and 20 on the y, so this skips up by 4 every time. which is convenient for our graph because our ticket prices we're going up by 2 ticket prices every time, which means our cost goes up by 4 every time. So it's actually pretty convenient to have this graph here. So we have 2 is 24, and 4 is 28, which is right there, and 6 is 32, and 8 is 36. So again, you're going to notice that all of these equations, all of these points are collinear, right? Meaning they all lie along the same line. So I'm going to pick that out here. And again, I draw the line into the edge of the paper. And I'm actually going to, which I should have done in the last one, write the equation on the line. This is a very good habit to get into. So I should have actually done it here too. X plus y equals 6. Okay, it's just a description of the relationship. So again, all the solutions to this equation lie along a straight line. Okay, and this has everything to do with the idea that this is a linear equation, meaning the value of x is raised to the first power. If this were x to another power, like x squared, we would actually be creating something called a parabola. We're going to cover that in a different module. Okay, a couple more questions here. Question number 1, does the point 2, negative 3 lie on the graph of x minus 2y is equal to 4? Well, think about it this way. If this point lies on the line, then it's a solution. If it's a solution, then I can substitute the x, y values into the equation to make the right-hand side equal to the left-hand side. Okay, so let's try this out. 2 minus 2 times negative 3 is equal to negative 4. We'd have 2 plus, this would end up being plus because you're going to have a negative 6 here. So here, we'll just write out 2 minus negative 6 is equal to negative 4. If I use KCC, it would be 2 plus 6 equals negative 4. And it is not true that 10 equals negative 4. Okay, whoops, that should be 8. That's still not true. So 8 is not equal to negative 4. So this is not a solution, right? So not a solution, therefore it does not lie on the graph. Okay. Last question, what must the value of d be if d comma 4 lies on the line? Well, let's substitute these values in. Except for x, we're going to substitute the variable d. For y, I'm going to substitute 4. So we have 3d plus 4 is equal to 10. So let's go ahead and solve this equation. We have 3d is equal to 6 divided by 3, and d is equal to 2. So d must be 2, because the coordinate must be 2 comma 4 in order to be a solution. Okay, so what we learned about today was we learned how to take solutions and create graphs from them. So we're looking at turning the algebraic expression of a function into the geometric expression. And we learned how to work backwards from asking whether or not a point lies on the line by thinking about it as a solution of an equation. And that's the end of the lesson for today.